Hi there, Turgeon here, bringing you Physics from Afar. Answers to the sound practice worksheet. Whenever a teacher gives you any kind of video, there's a lot to learn from that teacher, and people say, I'm confused. People say, I don't get it. Well, you got to start with listening. You got to start with getting that personal feedback from the teacher. Here it is. This is me explaining stuff to you. Make sure you do all these things. Listen, don't mute me, don't skip ahead, replay things. You're in control. In the year 2022, in my absence, you are taking a test on this. If it's not that year, then maybe you're just watching this video to get the answers to the sound practice. Notice what I did here for number 1. It says consider what makes up this type of wave. So I didn't particularly ask for the motions of the particles. I just asked for what the wave looks like, and this is what a sound wave would look like because it's air particles. Or these could even be particles of like aluminum or particles of water. It could be a lot of different kinds of molecules, but there's compressions. If you look back at the notes, sound is a longitudinal mechanical compression wave, and that's that you can see the wavelength between these compression regions. Looking up speed of sounds, there they are. Google that. You're going to see a lot of these. What is the wavelength? And you have numbers. So you're going to use v equals lambda f. Remember, v is the velocity of the wave as it's going through space, like from point A to point B. This upside down y is lambda, which is the wavelength, which is measured. In this case, the wavelength would be from this point to this point. You can see I tried to make that roughly equal from this point to this point as well. F is the frequency, not the frequency of the wave, because the wave doesn't have a frequency. It just shoots through space. If I speak, the sound waves are going through space. They're actually leaving my mouth and they're going in all directions. They're leaving my vocal cords and they're spreading out in all directions. If my dog barks, or you might hear the wind blowing behind me on this windy day. F is the frequency, not with which it's doing that, because that's just the velocity. F is the frequency with which all the particles are vibrating. So if I talk in a higher pitch voice like this, my vocal cords are vibrating faster, and the air particles were vibrating at that same frequency, and my dog, who can hear me, his eardrums are vibrating with that same frequency. You get 2 different answers for the wavelengths because the speed of sound does affect the wavelength. Remember that, simulator. These 2 sounds, the point of question B was actually to point out that you're going to hear them as exactly the same sounds. Now, I put a little asterisk because there might be some subtle differences in like the way that they are perceived as you go through space on different days. The way different frequencies might be a little bit louder or softer in proportion to each other in the human ear, but that's more like human perception. Venn diagram, sound and light have some differences and they have some similarities. So sound is much slower. It's like somewhere between 330 meters per second all the way to 5,000 meters per second. Light goes at 3 times 10 to the 8th meters per second, which is like 300 million meters per second. That's ridiculously faster. It does slow down a little bit when it goes into water or when it goes through glass and stuff. Light is usually higher frequency, like, I don't know, it might be like 6 trillion hertz, whereas sound that we hear is often much, much lower frequencies. I think we hear up to like 25,000 hertz or something, depending on the person. Sound is mechanical, which means it needs a medium. Light is electromagnetic, which means it does not need a medium. Light is transverse, which means the oscillation is perpendicular to the wave velocity, and sound is longitudinal, which means the oscillation is parallel to the wave velocity. So in sound, the particles might be oscillating back and forth. Oh, I told you not to say back and forth. In sound, the particles might be oscillating like this, and the sound wave is actually going like this. Those 2 are parallel to each other. In light, the particles might be oscillating like this, and the sound wave goes like this. But light doesn't always have to be particles. It's electric and magnetic fields, actually. Sound tends to be lower frequency. Light can be super, super high frequency. So both of them, though, they can reflect and refract. So reflection is bouncing off of a surface or a mirror or a wall or something like that, and refraction is when it bends. They both have this relationship where their frequency and wavelength are related to the velocity. Remember, every equation in physics is a relationship. And remember this, we're taking extra notes. I'm saying a lot about sound, so you can write that onto your paper because we're studying for the test. Light is ridiculously fast. I went over a lot of those. Here we go. Sound, here's a fuller description. So just to read it out loud. So it starts with a vibrating object, and then it transmits energy to the particles, and those particles have the same pitch, same frequency, all the way till they get to their various receivers. In this room, I've noticed in this room with all the windows, like I've been outside while there are a group of people inside, I can hear what they're saying. So it's transmitting through the windows as well. The windows are vibrating from the sound of my voice. And it spreads out in all directions, which means that the loudness is going to decrease, because as you get further away, you're going to have less energy as it gets spread out. Here comes a bunch of V equals lambda F questions. So you just have to recognize wavelength and frequency. In this case, I multiplied and they asked me for the velocity. In this case, I divided because they were asking me for the wavelength. You put the numbers in, velocity, frequency. You got to be able to do that on your calculator with scientific notation. Divide by 8 times 10 to the 12th. In this case, you were given the wavelength. Divide both sides by 500, get 600,000 hertz. If a sound is high pitched, you want there to be a lot of wavelengths in a short space, not to be confused with this. This is not very many wavelengths, and the amplitude's really low, so it's not a high energy sound, so it's not loud. This would be much louder because it's got a greater amplitude. You didn't actually draw a sound wave because sound waves don't look like that. You drew a graph of the microphone as it was oscillating. Remember how sound goes slowest through gases? Well, that means it goes air, water, steel. Number 12. We're using V equals lambda F. Plug it in. There's your answer. 12, 13, 14. You're just using V equals lambda F. You just have to know that hertz is frequency, M is meters, which is wavelength, and meters per second is the velocity. If the anchor is banging on the sides, here's what they're getting at in this MCAS question. The water and the sound waves, they're both mechanical waves, but one of them is longitudinal and one of them is transverse. That's just what they're getting at. I mean, I'm helping you with this. So if you can see, like, the sound particles are vibrating, and their vibration is parallel to the way the wave is actually traveling through space. They're saying, how would you measure this for the waterways? Well, you could, like, if it were me, I'd like put a meter stick near the waterways and I'd take a picture, and you'd be able to see from wave to wave. You'd be able to look at, like, oh, it was from like 12 centimeters to 22 centimeters, so it's a wavelength of 10. But you wouldn't want to measure from one crest to the next crest. You could measure from one trough to the next trough. That would just be harder to see. Okay, so that's the sound worksheet answers and explanations. This has been Physics from Afar.